For the next topic, we're going to take a look at radio frequency or RF fundamentals. So we're going to take a look at a number of different RF principles. We're going to begin by looking at the electromagnetic spectrum, frequency and wavelength, and how each determines the other. We're going to take a look, we'll actually look at how each determines the other in the next section for RF math, but thought I should go ahead and note now that one does directly determine the other. We're going to take a look at something called amplitude, something called free path loss. We'll take a look at the phenomena known as absorption and reflection. We'll also look at multipath and how a wireless signal, really any radio frequency or even audible frequency, has something called phase. We'll take a look at something called scattering. We'll also take a look at refraction. And we'll take a look at line of sight and something called the Fresnel zone. And then also, finally, signal level, also known as RSSI, or Received Signal Strength Indicator, and then noise. And I really find it best on this particular module to go to the whiteboard, and we're going to pull up a few images on the whiteboard, but a lot of times we'll be doing some drawing. So let's go ahead and switch over to our whiteboard. And to begin with, I want to take a look at the electromagnetic spectrum. So, and I actually have a little bit more than the electromagnetic spectrum here. But the idea is that we want to take a look at frequency. So if I take a look actually at beginning with audio, sonic, and ultrasonic, these really are not a part of the electromagnetic spectrum. The idea of the electromagnetic spectrum is that it's something that can exist in a vacuum, and sound cannot exist without air. Sound requires reverberation, or it requires vibration. And of course, if there's no air, there can be no vibration or reverberation. So while I have it on here, it's more just to show its relevance to frequency. So if we start down at hertz, we should really first just define what a hertz or hertz is. It's really not a hurt. The man was named Hertz. Like most things, we named it after a particular individual that figured this out. But hertz is a cycle per second. So 1 cycle per second is 1 hertz. And the idea is that we typically have the audible hearing range from about, some would say 20 hertz, although that's really something that's better known as the LFE or low frequency effects. You more feel those than you do hear those. But from about 20 hertz all the way on up to about 20,000 hertz. Anything above 20,000 hertz is the ultrasonic range. Some animals can hear those. Humans can typically not hear anything above 20,000 hertz. Depending on how old you are, you might not even be able to hear anything above 12 or 15,000 hertz, probably 15,000 depending. As you age, your hearing deteriorates based on various things that really aren't relevant to what we'll talk about today. But once we get into roughly just before the 100 megahertz, right around the basically 900 kilohertz to 1 megahertz range, we get into radio waves, and then we get into the actual electromagnetic spectrum. So the electromagnetic spectrum consists of radio, microwaves, infrared, visible, ultraviolet, X-ray, and then the gamma ray. And as we go along in the electromagnetic spectrum, as we climb into megahertz, gigahertz, terahertz, petahertz, and exahertz, the length of our radio waves gets on orders of magnitude smaller. So when we're back at the audio frequency, again, not necessarily part of the electromagnetic spectrum, but for the sake of discussion on frequency and wavelength, when we're back at the audio spectrum, if we're looking at maybe, say, a 1 kilohertz frequency. That's a very standard male and female average speaking voice frequency, right around the 1 kilohertz. Women tend to have higher frequencies that they hit, most notably in the 6 to 9 kilohertz. Males typically have a little less, 900 to 4 or 5. Just depends on the person, of course, kilohertz. But at any rate, right around the 1 kilohertz, we're talking about a wavelength that's roughly 62 miles long. Okay, and apologize if you're deal in kilometers. I don't know exactly what that would be in kilometers. I think it would be roughly 40 kilometers. Anyhow, very, very long. When we get up to things like visible sight, okay, when we get up to things like the visible sight range, we're talking about wavelengths that if you took and held your arms out into kind of formed a circle and made it as big as you could possibly hold your arms, that would represent the width of a hair. And then if you took your finger and dotted the smallest dot in the middle, that would be about the width of the actual frequency for visible sight, depending on where we're at, right around the 100 terahertz range, actually slightly higher than that. 100 terahertz is still in the infrared range, not quite. I guess no, it does hit into the red area, but so that's just a general kind of visual conception, kind of something you can do in your mind to conceptualize how tiny the wavelengths are for visible sight. Or as we get on to gamma rays, we're talking so small, and actually that's why we really have a limitation to this, is once we get up to the 100 exahertz range, we're getting on the order of, beyond almost the nucleus of an atom in terms of how tiny these wavelengths are. And I'll actually give you a little bit later a calculator that you can go to online and actually put in any frequency and get back the wavelength, or put in the wavelength and get back the frequency. In fact, the calculation is fairly simple. We'll talk about that in a little bit. But wireless networks that we're dealing with today are on the range of, as we mentioned, they tend to be either the 2.4 gigahertz. We do have the old 900 megahertz, so just before 1 gigahertz, but those aren't really what we use today in any of our 802.11 specs. So either 2.4 gigahertz, right in the microwave range, or in the 5 gigahertz, or as we mentioned, soon to be in the 802.11 AD, roughly right here in the 60 gigahertz range. Okay, so this is frequency. When we talk about, and as I mentioned earlier, when I talk about bandwidth, I'm going to be talking about how wide a particular signal is. So if I have, let's just choose a color here. If I have, let's say, 2.4 gigahertz, or actually, we'll probably refer to it more in megahertz. So if I have 24, let's just give an even number here, 2400 megahertz, or 2.4 gigahertz even, and I say that I have a 20 megahertz wide channel, then I'm basically talking about from 2400 megahertz to 2420 megahertz, or 2.400 gigahertz to 2.420 gigahertz. Okay, that looks more like a Y than it does a 4. But that's what we're talking about when we talk about bandwidth. How much width or how wide is a particular frequency spectrum. So moving on, let's talk a little bit more about frequency in hertz. So as I mentioned before, a hertz is one cycle per second. Okay, so if I have, let's just bring back up my drawing materials here. If I have a wave, and really the idea of wavelengths can be very commonly and is commonly given the analogy of, let's just say, waves on the ocean. Okay, they operate in really the same way. So if I have a wave on an ocean, I've got a peak, and I've got a valley. And it's not exactly a perfect wavelength, but I've basically got the peak here, and I've got the valley. And the distance between two peaks is going to be one cycle. Okay, so I've got one cycle here. So that's oscillating one time in 1 second. Here, I've clearly got 3 peaks, even though this one is kind of at the outskirt here. So I've got 1, 2, 3. This would be 3 hertz, or 3 cycles per second. As I need to have more, and I should actually go back and say, imagine that from left to right here, okay, imagine the width of my screen is the time frame of 1 second. In fact, more than just imagine. We'll just draw it. That is 1 second. Okay? So if that's the time frame of 1 second, and I realize I didn't start quite at the left edge, so we'll just make this our pretend left edge here. But if that's 1 second, and I want to have a different frequency, then I'm going to have a smaller wavelength, right? So if I want to have, let's just see what we come up with. 1, 2, 3, 4. So let's say I've got 1, 2, 3, 4, 5. I've got 5 cycles per second. The length between these two, the length between the waves, or the wavelength, is a shorter distance, but now I have more cycles per second, or a higher frequency. So these are inversely related, right? If I have a higher frequency, I'm going to have a shorter distance between the peaks of the wave. I'm going to have a shorter wavelength. If I have even, whoops, too far down. If I even have a longer or higher frequency, so let's say I want to, we'll just stop it here. If I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I realize that's not a perfect wave by any stretch of the imagination, but if I have 10 hertz or 10 cycles per second, then my wavelength, although this is a lot longer than this, and in a perfect world, these would be exactly the same. Each of these lengths between the waves would be exactly the same. I would have a shorter wavelength, but a higher numerical frequency. Okay? Now, it also should be noted, as I really mentioned before with audible, even though, again, audible sounds are not part of the electromagnetic spectrum, they still do have frequency and wavelength. With lower frequencies, so if we're just talking in the radio or microwave range, the beginnings of the electromagnetic spectrum, lower frequencies travel further in the air than higher frequencies. And if you think about it, that just makes sense. If I have a lower frequency of 3 hertz, it's going to travel longer to complete its cycle. From here to here, it's going to travel a longer distance to actually complete that cycle. Now, you might say, well, wait a minute. Mark, you mentioned before that 1 kilohertz, and don't hold me to this exact number, I'm giving you a rough estimate, but 1 kilohertz for audible frequency goes, roughly 62 miles in wavelength. So how come if I just talk, someone doesn't hear me 62 miles away? First of all, again, the audible frequency that I gave the example of isn't in the electromagnetic spectrum. It cannot exist in a vacuum. So we have disruptions, like the very thing that transmits the vibration of the air is also the thing that disrupts it. And we're going to talk about more things that disrupt traditional radio frequencies, such as wireless LANs, here in just a moment. But the idea is that we have things that disrupt the signal. So whether we're talking about the audible range or whether we're getting back into, and the only reason I'm drawing 3 hertz or 10 hertz is because I really can't draw 2400 hertz at all in this screen, much less with any degree of integrity. Not that these are highly, have a high degree of integrity for the distance between these existing waves that I've drawn. But at any rate, there are going to be things that interrupt them, even in those higher frequencies. So to say that something has a certain wavelength, first of all, as we get higher in the numerical frequency, we have a shorter wavelength. So we have the more likelihood that these things will complete at least one wave, probably many, many, many hundreds or thousands or even millions of waves, individual waves, before that transmission is sent. But at any rate, even if we're just looking back here at the lower end for the sake of example, there's nothing to say that this wave that starts out here is necessarily going to make it all the way to its completion. Here's where it might complete and continue on, but nothing's to say that it will make it the whole way. And that's part of what we have to deal with in wireless networks, is to ensure that we have the best possible environment to allow our waves to transmit as far as they can. Okay? Or possibly limit them from traveling as far as they can and limit them to a very specific area that we want them to transmit in. Sometimes the idea isn't to try to make your signal go as far as you can. That's normally your intent if you're maybe just a personal user at home setting up a wireless network for your house or apartment or flat. But if you are a corporate environment or maybe a convention hall, maybe you don't want any wireless connectivity out in the halls. My mind is obviously always brought to Cisco Live, where as you're walking into the breakout sessions, if you're in the general areas, whether it's the world of solutions or whether it's the common break areas, there's typically wireless connectivity. If you're in the halls in between where the actual breakout sessions are held, you almost can't get a signal at all. And that's done with intention so that people don't loiter outside the rooms and cause disruption for the speakers and listeners of those breakout sessions. The moment that you step into that room, you can get an immediate, very high quality wireless signal. And so sometimes the idea, getting back, isn't just to propagate the signal as far out as we can, or necessarily sometimes what we want to is just to be able to limit that signal. But anyhow, frequency and wavelength. Okay. Also, it should be noted that waves always travel at the speed of light. Okay, roughly 299 million meters per second. Okay, so that's some people round that up, especially when doing a very quick calculation, not necessarily for tuning a particular, creating a particular wireless device. Obviously, you would use the exact figure, but some people just round that up to 300 million meters per second when doing a quick calculation of light, the speed of light. Okay? And again, down in the audible spectrum, not in the range of electromagnetic spectrum, so therefore that is not sent at the speed of light. It's sent at the speed of sound. In the electromagnetic spectrum, beginning with radio waves and then moving on to what we are dealing with, which is microwaves, that is sent at the speed of light. Okay, so let's take a look next at the idea of amplitude. So we're going to draw our waves out again. We're going to do it in a little bit of a different fashion. So if I take a look, first of all, let me actually create in a little bit of taking up a little bit less real estate, some of these same, let's do 3 kilohertz. Let me draw that a little bigger. Okay, so we've got 3 kilohertz, 0.1, 2, and 3. And then we're going to have, let's say I want to look at that same 3 kilohertz, but I want to look at a higher amplitude. Now, if we were talking about sound, and the reason I keep bringing everything back to sound is that a lot of times people can relate to sound better than they can necessarily relate to the abstract, ethereal concept of radio waves. So I'll always bring it back to radio waves, but sometimes it's easier to think about with sound. If I think about sound and radio waves, if I'm talking about amplitude, most people would refer to this as volume. So how loud is the signal? The same thing occurs in wireless networks. It's just that we can't audibly hear it. And in fact, it's really a misnomer to call an audio frequency even volume. Yes, we can hear something louder, but really it still has to do with amplitude. How much power are we giving to our wave? So if I had 3 hertz here, and we're going to take a look at the bottom and the top of that wave, this writing pad isn't the easiest to use. This right here is my amplitude, okay? The vertical direction here. So if I were to create this same 3 hertz, but I made it like this, I've still got peak 1, 2, and 3. They're roughly about the same distance apart from each other, roughly the same wavelength. Again, they would be exactly in an ideal world. But my amplitude is obviously much higher. I have a much greater vertical distance. I have powered or put more power behind the transmission of this wavelength going out, or of this wave, this sinusoidal or sine wave. Okay, so let's say I come down here. That was almost the same. Let's make it even a little bigger. I'll go back and make that next one a little bigger. Or sorry, that first wave. So assuming that these were exactly the same wavelength, and I realize that I am far from perfect here, but I still have 3 hertz. I still should have the exact same wavelength. That is the exact same distance from left to right. Yes, I realize it came out a little bit far. But the volume, for lack of a better term, or if we have the better term, specifically what we want to talk about, amplitude, is much higher. Okay, so the amplitude of a signal, not amplitude, amplitude. The amplitude of a signal is basically that height between the waves or between the crests. So for any same wavelength and frequency, again, frequency determines wavelength, wavelength determines frequency. Those are indirectly related. The higher the frequency, the shorter the wavelength, or conversely, the shorter the wavelength, the higher the frequency, or I could say that in the reverse as well, that the longer the wavelength, the lower the frequency. At any rate, for the exact same any given wavelength and frequency, there can be different amplitudes or different levels of power, quantities of energy that are used to inject that signal into the air, into transmission. Okay? And that's typically regulated by different regulation or regulatory bodies that we'll be taking a look at later, because of how much power it can put out, how far that wavelength can go, how many other devices it can cause interference to. Oops. So next we want to take a look, going back to our list of what we want to take a look at here. We want to take a look at something called free path loss. And this is actually a fairly easy concept to understand, because as most people do, I'm going to use the same analogy of a very calm, crystal clear lake. If I have, some lakes are even nicknamed glass lake or mirror lake because they have just a pristine top. There's nothing affecting the top of it. if I take a look at a lake and I toss a stone or a pebble or a rock or a boulder, depending on what I toss, will depend how far, really it will depend the amplitude and the length of the wave that is created. And if I toss it sufficiently far out from the edge of that lake, I'll be able to see in a perfect radiating circular pattern the idea of, tell it to draw here, of not only the part where I tossed it, the very middle, but I'll also see waves emanating around it, almost in a bullseye, and you can tell I'm not the drawer or artist in the family by any stretch of the imagination, especially with this particular pad. Wow, that was really bad. I'm just going to erase that one. But we begin to see this wave emanate out from the center. And as it comes out from the center, the lines get weaker and weaker and weaker. And I'm trying to draw put very little pressure on to get the thinnest possible line until we almost don't see that wave at all anymore. Okay? That's a horrible drawing. I realize that. I apologize. But the idea is that as we get further out from the edge, something called free path loss occurs. Free in the sense that there's really not much affecting the signal other than distance. Okay? And depending on the size of the rock, which we could basically say is analogous to the amount of power that we put into the transmission of our wireless signal, or the amount of energy that we put into the wireless signal. Depending on the size of that rock will depend how big the wavelength was to begin with, how much distance was between each wave, because each of these are a wave, as we talked about, going out. And they don't get, or they should not get any larger as they go out, even though my drawing tends to look like they're getting larger. But what they will do is they'll weaken. So as they go out from the middle, they'll begin to get weaker and weaker and weaker until all of a sudden they just can't even transmit any longer at all because there's just nothing there anymore. I'm trying to put as little pressure as I can. And that is the idea of free path loss, that as the signal travels outward from the source, from the transmitter, given the frequency, so therefore given the length of the wave, and also given the amplitude, there will be a disintegration to the point of nothingness of that particular wireless signal. That the signal will essentially completely disintegrate. Okay? Then we have to look at the idea of absorption. Now, with absorption, what we have is we still have this wireless signal, but we're going to have devices, or we're going to have really just construction materials in our way, no matter what that is. Whether we're outdoors and there's a building in our way. Typically, when we're talking about wireless LANs, we're most of the time talking about indoor, but we certainly will talk about outdoor some. If we're indoor, we have drywall or plaster walls. Typically in corporate environments, we have drywall. We have various ceiling tile properties. We have books, especially in libraries or, law offices, universities. We're going to have desks made of wood. We're going to have metal studs in between those walls, in between those drywall walls. And all of these different construction materials have different effects on a wireless signal. If we have, let's just say, a drywall wall, and in between there, and this is actually kind of a cross-cut view, so this is a side view, But in between there, at various points, we're going to have, in a corporate environment, probably lightweight steel studs. We are going to have this signal absorbed by the drywall. And so while the frequency and the wavelength will not change, the amount of amplitude really will somewhat change, somewhat be absorbed, so that the wall is going to absorb some of that signal, and it's going to decrease the amplitude. It's going to decrease the height of that signal. It's going to decrease the power of that signal. So we need to take into account the effects of the building materials. And while we're going to talk to some degree about something called decibels in a little bit, probably in the next section called RF math, and we're going to talk about a little later on how some of these building materials can specifically affect the decibel or the power ratio of a given wireless signal, we're not always going to be able to precisely account for every given situation in a corporate or even home or even outdoor environment. So in other words, there's not going to be an exact mathematical figure or algorithm that can be run to say this is exactly what you will need for your environment. Now, there are really great estimations. We're going to take a look at a planning tool very briefly in something that Cisco calls the Wireless Control System, their WCS, a lot later on. And it has the ability to estimate. But even then, and even when you move on to your CCNP wireless and you go into the site survey particular series of learning modules as one of your 4 tests or exams that you have to take for your CCNP wireless, they're going to tell you, and you're going to note that you can't calculate exactly for that. You're always going to have to take and do always something called a site survey, where you physically walk around with some sort of handheld device, most probably a laptop, but we're getting more and more mobile with iPads don't necessarily let you have full control of their wireless radio, so the apps can't truly do what they need to do. Android does allow that, and there are certainly some apps that are being developed for that. But you have to take some sort of a wireless client, typically, historically a laptop, and walk around and actually do the calculations, let the access point and the controllers do the calculations to see precisely how that wireless signal is going to affect and be affected by your physical environment. So the topic of absorption and a number of the other pieces that we're about to talk about that really destroy or attenuate your signal are things that you have to keep in mind when deploying a wireless network. I use the word attenuate. Attenuation is the loss of a signal across a given medium. In this case, our medium is air, okay? And the signal is a wireless signal. But attenuation is the loss of that signal, the loss of amplitude or the loss of energy. Again, frequency and therefore wavelength are always maintained. Okay, so taking a look at the next topic, we're going to look at something called reflection. So as I have let's draw a desk here. This is just, let's just say this is a crude desktop, kind of on a flat surface, so the legs are maybe going down underneath. And I've got, so we're kind of looking down from the top. Maybe I've got a door over here. I realize the dimensions of my, maybe I've got some lights in that door. I guess that's more of a home door than it is an office door, but at any rate, you get the idea. We've got a door here. We've got some metal studs in the walls. Okay, so these are the metal studs in between the drywall. different properties, different physical properties or building materials inside of any given environment are going to cause reflection. Now, reflection, of course, is where light or some sort of electromagnetic wavelength is transmitted, is reflected, is mirrored back to you. The best example of a reflection is, of course, a mirror with visible sight where we look into it and we see ourselves back in almost a perfect example of ourselves. But so with reflection, I might have a wireless signal that's coming down here, and we're going to talk about polarization, we're going to talk about angles, we're going to talk about types of antennas, and so where these wireless signals are being directed, whether they're being directed or whether they're emanating out from the center perfectly in a circle, which there is no perfect circle, but theoretically in a perfect circle, something called omnidirectional. But at any rate, these signals are going to be coming down, and as they hit something, they're going to be reflected off of that surface. So I'm trying to maintain my same wavelength and frequency, but the idea is that a signal is going to come down and be reflected off. So the reflection, or as we're going to talk about a little later, refraction, but reflection right now really depends on the roughness of the given material and how that is relative to the wavelength, the length of that wave, and the angle at which it's being reflected. Okay? So for instance, if I had mounted a AP, well, let's just say this is the wall here, this is the drywall on the outside, and there's my metal stud in the middle. If I had mounted an AP on the wall out here, and I had put, my antennas are sticking up, then I'm going to have wavelengths that are coming out from that antenna, but I'm also, assuming it's a omnidirectional antenna sending it in all directions, it's going to come back here, and some of it's going to transmit through at a lower amplitude. Some of it is going to be reflected off. It's one of the reasons that most manufacturers will tell you not to mount your device directly next to a metallic surface, and if you have no other choice, to make sure that the length between the antenna and that surface is at least one wavelength. And we're going to talk about the distance of the wavelengths for 2.4 and 5 gigahertz a little bit later, because that definitely affects the positioning of antennas. We don't get too far into that in CCNA wireless. That is covered very in depth in the CCNP wireless, especially with site survey, but we will talk about that a little bit, because the distance of the wavelengths for 2.4 and 5 gigahertz are not nearly as small, not even remotely as small, as we were giving the examples of with visible sight earlier, where if I had the diameter of a hair was as big as I could possibly hold my arms out, then the wavelength, the visible sight, was a tiny speck in the middle of that for proportion. Here we're talking about inches or centimeters for 2.4 and 5 gigahertz respectively. Okay, so that's the idea of reflection. We also want to take a look at something, since I have my environment set up here, we want to take a look at something called multipath. With multipath, oops, click back on my drawing here. With multipath, we have the possibility that, wrong thing, we have the possibility that signals are going to be sent in multiple different directions. So again, I have my AP, and it's, let's say my AP is over here, because that's where we started earlier. Got my AP and antenna, or possibly two antennas, possibly three. We'll talk about how many and why later. But as I'm sending a signal out, it's not only hitting one device and being reflected off of, but it's very possibly hitting multiple devices. So maybe I also have a desk over here, and I also have a ceiling. So this signal is being, and I'll just use a different color here, this signal is being sent and reflected off of this surface, reflected at a different angle off of this surface, sent and reflected at a different angle off of this surface, and it's being received by the client, depending on where the client is. Maybe the client's over here somewhere. It might be being received by this particular reflection at one point in time, and it might be received by this particular, of course, it's not really on the path, but let's just assume it was. Maybe my client's a little larger. It's being received by this particular path of the signal, multiple paths, at a later time. And it's not being received by this particular path. It might be coming out here directly and received the fastest before anything that is reflected off of another surface. So multipath occurs when a signal reflects from different surfaces and those signals arrive at the given receiver or client at different times. Again, this depends on the wavelength, the frequency, and also the position of the receiver. But the thing is that we're getting quite possibly multiple copies of the same transmission signal. So the client needs to know how to deal with this. In older networks, we would take the first one and we would probably just throw away the older ones unless they had a better signal strength. Now, typically the first signal that would be received would also normally be the best signal strength, but not necessarily. So normally we would take the best signal strength in the first and use that. But as we'll see, as networks have progressed, as technologies have progressed, people have done things to realize that this phenomena is going to be there, and so try to utilize it rather than eschew it. Rather than try to get rid of it or hope that it doesn't interfere with us, they've tried to embrace it, and some really good things have happened. We'll talk about that more a little bit later, but just keep in mind that idea of multipath. We also want to talk about something called phase. So I talked about, let's say I've got a wave here. So I've got a 3 hertz wave, and I can see that my peak is here, my trough is here. Peak, trough, peak, trough, right? If I were to have a wave that went like this, is that not still a 3 hertz wave? Let's just say it doesn't go all the way down, okay, just to be safe. So I've still got peak number 1, 2, and 3, and trough number 1, 2, and 3. It's still a 3 hertz wave, given this, these two horizontal boundaries being the time of 1 second. Okay? It's still a 3 hertz wave, but these, and this is going to be very important as we begin talking later about modulation techniques. It's going to be very important that you understand what phase is. So these two waves being the exact same frequency, having the exact same wavelength, are 180 degrees out of phase with each other. Okay? If you've ever set up, again, I'm going to go back to sound because it's easy to comprehend. If you've ever set up a home stereo system, and especially if you've set up, let's say, a subwoofer in kind of a higher end home stereo, a lot of times the subwoofer, which is self-powered, will have a switch on the bottom that says, or somewhere on the back that says phase, and it will say 0 or 180. The idea is that if you happen to be out of phase, you're going to hear, let's say, the amplitude of this volume, or sorry, the amplitude of the signal, the volume, kick in right here at this point, and then you're going to hear maybe the bass later. And because these are happening so very quickly, so many thousands of times per second, it's going to, or at least 10 or 20, 80 times per second in the case of bass, very low end frequency, you're going to hear, it's almost going to be like you're just going to feel like something's not quite right. Like everything seems just kind of off. Okay. And the idea is that the signal from your tweeters and your standard speakers, your standard woofers and tweeters are getting there at one time. And the audio from, basically because of a miswiring, because you reversed polarity, from your subwoofers are getting there at almost the exact opposite time as the peaks of your tweet, of the high frequencies. And this is called being out of phase. So this is 180 degrees out of phase here. We're going to talk later about 90 degrees out of phase. So if I have 90 degrees out of phase, I basically have something that looks roughly like this, where I've got basically something similar to that. 180 degrees out of phase is going to be exactly opposite of that. Okay, so we've got 90 degrees out of phase, 180 degrees out of phase, 270 degrees out of phase, which is really just 90 the other way, or negative 90. Okay, so this would be 270 degrees out of phase from this. But we've got this idea that the signal, the peaks, are arriving at different times. So if I have something that's in phase, let's just go ahead and erase this. If I have something that's in phase, then it's going to be like this. Now, this is very important when we have multiple paths. You might say, well, wait a minute, why are we talking about in phase and out of phase? You only have one wireless signal. You do if you're only hearing one wireless signal. But again, the phenomena known as multipath is going to occur. When it occurs, that is to say, when a client, let's say a client on my laptop here, when this client gets their signal from a given access point with radios, is that signal that has reflected off of things, are these different signals, are they going to be in phase or are they going to be out of phase with each other? And if they're out of phase, how much out of phase? If we have two different antennas, maybe we're sending the signal off, two different signals off, something we'll talk about later called diversity. Maybe we're sending a single signal, but then we're stopping the transmission of the signal, and then we're starting the signal back up again. So we're actually sending a signal, then we're stopping it, then we're starting it back up again. The same signal can be in or out of phase with itself. How is that possible? Well, let's say if I have, let's just draw this right here. And I realize my wavelength is getting longer as I go on with time, which is not physically possible in RF, but in a bad artist, it's very possible, like me. But let's now say the green, so the red is the theoretical signal, where it would be if it had not stopped. The green is going to be my actual signal, where I stop, and then I start transmitting again. And notice how when I stopped transmitting, I started transmitting again halfway down, basically 90 degrees out of phase. So instead of actually transmitting where I should have and continuing to come down there and then back up, I stopped and I started again 90 degrees out of phase, or possibly even, let's say, 180 degrees out of phase. So the idea of wavelengths and those waves being transmitted, stopped and started, or multiple waves being received at different phase from each other is an extremely important one to understand. Okay? Look back at our topics that we wanted to cover. So we've talked about absorption, reflection. We've talked about multipath and now phase. We want to look at scattering and refraction. Scattering is something that is probably easiest to demonstrate or talk about if we were, let's say, talking about outdoor wireless. It happens indoor as well. And one of the things that really affects or causes scattering more than anything is humidity, moisture in the air. Believe it or not, the moisture that's in the air or the lack thereof can dramatically affect your wireless signal. So first of all, water is very dense. It's not that easy, especially if I have a large body of water, let's say a lake, to transmit a wireless signal. Okay? That water being a very dense material, very compacted together, is going to cause my signal to degrade dramatically. And even the humidity in the air, tiny particles of water in the air or tiny particles of dust would actually cause this as well, are going to, let's say I've got, let's just say I've got particles of water. Some of these particles are larger than others, clearly. But I've got particles of water everywhere in the air. And I suppose in real life, some, especially if it's raining, would be larger than others. So I guess that works for the analogy. But I have an access point and the radios, and it's transmitting its signal. And as it goes along, it hits a piece and it bounces off. And this signal hits another, maybe I've got a second signal coming out here and it hits and it bounces off. So I've got all this scattering going on. The higher density of dust, especially like in a manufacturing environment, if I'm on a, factory floor trying to install access points, this is going to become an issue if it's not a very clean, and by that I mean dust-controlled type environment, or in levels of high humidity, either indoors or particularly outdoors. This is going to affect how my signal is going to scatter off of these bits of dust and water molecules. Okay, so the idea of scattering is really almost one of reflection. And these could just be multiple signals that are being sent out. It could be the same signal sent out over time, hitting different particles. Okay, so over time, it's not that I'm sending out 100 signals, but as I'm sending out one signal now and then later and then an hour later, it's hitting a different particle of water, different particle of dust. And so it's going to be difficult to predict if that will get there in a perfect line. So one of the ways to deal with scattering is to minimize the amount of dust, certainly to minimize the amount of humidity in the water. But the idea of scattering is that it's going to cause that signal to reflect into all different areas. We also want to take a look at the idea of refraction. And the idea of refraction is probably easiest to demonstrate with a picture. So the idea of refraction is that I have, let's say, this cup here, and as you look at it with visible light, which as we know, visible light is part of the electromagnetic spectrum, just as our radio or what we're dealing with in our wireless lands, our microwaves are, we have the possibility that a signal, in this case light, not the straw, but light, enters a given medium, in this case water, and it appears skewed. So we have, it's not a reflection. A reflection, let's say off of a mirror, we're going to have, depending on the angle, if we're at more of a steep angle, then we'll have more of a steep reflection, but it's a whole copy of that signal being sent back really undistorted. It's just passing back off of a material. It's reflecting off of a material. With refraction, the signal is actually being distorted. Okay, we can see here that as we visibly look, I look at the straw, and then if I look at it, so just look at the straw through the glass, look at the straw through the air. It doesn't look like the glass is really affecting it from here to here too much. But as I look at it as it passes through water, the edge of it here and the edge of it here are they're very disjointed from one another. So it's dramatically affected the signal, in this case, the signal of light, or the signal of, I guess this is a pencil. I guess there's a tip down here, not a straw. At any rate, it would do the same thing. It's going to affect our microwaves as well. Okay, so the idea of refraction is something that we certainly need to consider in the same way that outdoor wireless networks with scattering are going to take effect with levels of decent humidity, with levels of extremely high humidity. We could even have refraction. So basically the wave changes direction altogether not in a reflective type way, but in a very drastically different way. Okay, so now we want to talk about something called line of sight and the Fresnel zone. Now this comes much more into play in outdoor networks. It can find its way into indoor networks, but typically only those of long distances indoors, maybe down. Really, this is much more about outdoor networks. I suppose line of sight can, as I began to mention, like down a hall or something, if we have something called a directional antenna, something that's sending our signal in a very specific direction, and we have some sort of obstruction, a very large obstruction. But as I mentioned, this tends to happen on outdoor networks much more. So this is the Earth here, okay? Just got fairly small. And I have business A over here. It's got its building, it's got windows, and it's got a parking lot, whatever. We put an antenna on the top. And depending on where we put that antenna, to probably some sort of a directional antenna, we want it to reach business B over here. Let's just draw business B right up here, where the curvature of the Earth has not had that much of an impact on it. And so we've got our highly directional antenna here, maybe even a parabolic dish, depending on regulation, meeting those regulations, depending on what you have available to you, depending on a lot of things. But the idea is that there's two things. One, the direct line of sight between these two needs to be good. But there's also something called the Fresnel zone. And the Fresnel zone is a 3D extending in all directions path that we're only showing kind of a two-dimensional horizontal above and below part of that Fresnel zone. But it certainly would come out here to the left and right as well. And the idea of this Fresnel zone is that the signal that we're sending and then receiving on the other side isn't, no matter how good we get with our antenna creation, it's not going to be a perfect line. And so the signal is going to emanate. Let's say this is our sender down here. The signal is going to emanate out like this. And so it's going to need to be received on the other side. And if we don't have enough of that path, called the Fresnel zone, available to the receiver to essentially, for lack of a better term, hear or listen to or receive the signal on, then we're not going to have a good quality transmission. We're not going to have a good quality signal. We're not going to have a good quality data rate. So what we need to make sure is that we have at least 60% of that transmission area, the Fresnel zone, available to us. So if, let's say, this inner line, this top green and bottom green line, let's say that represents, shouldn't have drawn another line there. Let's say that represents this bit here. Let me just color it in with yellow. This bit here represents 60%. Okay? And out here in orange, this represents the other 40% for a total of 100% of my Fresnel zone. if I don't have what's in yellow here, at least 60% available to the receiver in terms of line of sight, in terms of not being interrupted by something, then we could have a seriously degraded transmission. So let's say someone comes along and, let's say this happens to be, these buildings are, let's say 4 miles apart from each other. Someone comes along and in between those 4 miles, certainly it's not in any way unheard of that someone builds a building. And we happen to be in a downtown environment, center of commerce, so they build a very large building. And this is, of course, made out of solid materials, whether it's glass or whatever. They build a very large building. They've now disrupted not only the center of our transmission, but they've disrupted at least 80% of our Fresnel zone as well. And more importantly, as I just alluded to, even more importantly than the 80% of our Fresnel zone, they've interrupted that direct line of sight. Our signal will not work at this point. We will have such a degraded signal, if we get anything at all, that it will be worthless and not able to transmit a megabyte, much less 50 or 100 or whatever the spec may be, a gig, whatever. So what we would need to do is we would need to raise, if we wanted to continue our transmission, we would need to either build a taller building or most probably build a high mast on that building. And I realize the proportion of my mast to my building makes it look like the mast is about 150 feet tall and the building's maybe 20 feet tall. But let's just imagine that the mast isn't quite as tall. Maybe our building started out a little bit taller anyway. It's just for the sake of this particular drawing here. Maybe we add another story to our building. We add a mast and we put that antenna at the top of the mast. Okay? Again, just assume that this isn't actually so out of proportion, the mast with my building. Okay? Let's just add another story to my building here. So we add a mast and we have this higher antenna now. We've positioned it physically higher. So now our line of transmission is direct here. Part of it's going into the sky above what I can draw on this particular whiteboard. But let's say this is the 60%. Okay, we've got another ring outside that would represent the other 40%, but this is at least the 60% of our Fresnel zone, which has our waves going across uninhibited. So as things become in the way, if I have a very low, let's say I have a 1-story building or one level on my building, and I've got an antenna on the top of it, and we are just putting up just a parabolic dish or a directional antenna without any taller mast, okay, or pole, whatever you want to refer to it as, then even simple things like trees could get in the way of even a very short distance. So it's the reason that you see a lot of times, even if we're looking, let's just say at cellular networks, mobile phones, you see those cellular network radio antennas up on high peaks, high points, because they want them to be able to emanate and broadcast down to the earth where people typically are, and avoid as many obstacles as they possibly can. Because the line of sight, and again, the Fresnel zone, that oblong shape zone, extending above and below, extending out to the left and right, vertically, horizontally, diagonally, in 3 dimensions, if at least 60% of that line of sight is not available, your quality of your signal will be significantly degraded, and you'll have issues sending and receiving your information. Now, actually, before we move on, it's also going to be important, since we're talking about line of sight, to talk about just the curvature of the Earth by itself. If I have a building here, let's actually just, that's fine. Let's have my building here, and I've got my small antenna, and I've got a building here, and I've got my small antenna, you might, let's just say this distance is 6 to 7 miles. So what, roughly 3 kilometers, 3.5 kilometers, something like that. My signal, it might look like I have a proper line of sight, right? So, and by the way, 67 miles is about the limitation for the curvature of the Earth. What I'm about to show, let's actually say that this particular distance is maybe 8 miles, okay? Because I want to show how disruption, the curvature of the Earth could even be a disruption to this signal. It looks like I have a line of sight, but then if I consider my Fresnel zone, here's my 40% additional for a total of 100%. This is my 40% for a total of 100% of the Fresnel zone. And in here in the middle is my 60%. The problem is we get into the Earth actually blocking part of that 60%. So as you get out beyond 6 to 7 miles, as you get on to 8 or 9 miles, the curvature of the Earth begins to make it difficult, if not impossible. I say difficult to begin with, depending on the height of your building. Oops, wrong screen. Depending on the height of your building and then the height of your mast and antenna. Once you get out to, beyond 7 or 8 miles, it becomes impossible unless you have an antenna on the Burj Khalifa or something like that. The tallest building in the world. But unless you have something like that, you're getting into the curvature of the Earth, beginning to make it an impossibility to transmit. And so this is where people either have another building in between, or they lease space on a roof of another building, and they essentially have a repeater. So they broadcast up here, and then they broadcast down here, or maybe they lease space at the top of Carrier X's, high antenna mast, where they can broadcast down. If you're in a mountainous area, a lot of times carriers will own certain areas of that, geographic land. And the reason you might want to lease space from them, or simply build your own, the reason you might want to lease space is because you can utilize some of their radio shacks, their little buildings at the bottom of the actual antenna, that you don't have to go create your own building, run power, run backup generator, etc., but just lease their antenna and their radio shack at the bottom, where you can house your components, your AP, and then have your antenna go up and redistribute or repeat your signal even farther. Okay, so those are things that are important to think about when we're talking about line of sight, the curvature of the Earth, and obstacles in the way of the Fresnel zone. So let's take a look finally at RSSI. I realize we're going just a little bit beyond an hour, but let's take a look at the last topic of our fundamentals of RF principles, which is our received signal strength indicator and something called noise, and then how that affects our signal. So if I have a, let's say I've got my wave here. Oops. We'll probably use a 3 hertz wave quite often. So here's my time. I've got 1 second. And again, we talked about how my power was indicated by the height of the wave. And what did we say that power was? We said it was amplitude. Okay, so I've got my amplitude. The problem is that with any given signal, in our modern day times, we're going to have noise. So let's say this is the same frequency, okay, so the same wavelength, but I've got all sorts of different transmissions on that same frequency So if I was looking at my green signal, I'm just kind of coloring in the waves here, the high peaks. If I've got my used orange signal, again, coloring in the peaks, again, 3 hertz, same wavelength, same frequency. And my magenta, coloring in the peaks. And then I go back to my black. Okay? You can see how all of a sudden the amount of space, depending on phase, depending on frequency, the amount of space that this is actually able to be heard is diminished. So maybe my amplitude or my overall strength of my signal is, this high, but really I've got all of this noise. Let's just use orange here. Up to about here, I've just got noise. And we could almost, if I had a bigger one, just say, depending on how loud this noise is, it's just like trying to talk in a very crowded room where there's a lot of people that are talking, not necessarily your same language, not necessarily saying the same words, but using the same frequencies of their voice. If I have someone talking at a very high frequency, let's say 9,000 kilohertz, 9 kilohertz or 9,000 hertz, or I have someone, and I also have someone talking, let's say at 1 kilohertz or 1,000 hertz, then those two different frequencies are going to be fairly easy to distinguish between each other because of the different sounds, the different tonality of that voice, right? The different wavelengths or frequencies that they're transmitting at. The amplitude of those are also going to play a factor. The volume, how loud is that, let's say, woman that's talking at 9 kilohertz and the man that's talking at 1 kilohertz. Okay, how loud is that? Let's just say we're the man, I'm a man. How loud is that woman talking? Even if she's talking very loud, the difference of the frequency will probably still make it so that I can hear a little bit or most of what I'm saying. She could get so loud that it will be hard to hear at all. And so this is where different frequencies can very much cause a problem, even with something that we'll talk about later, adjacent channel interference. But different frequencies can even cause a problem with our hearing or receiving the signal. But if they're on the same frequency, if we have two men talking both at 1 kilohertz and one is talking very loud and we're talking fairly loud, but he's across the room and he's using up almost half of the available listening frequency, listening power, listening spectrum here, then it's going to be very difficult to hear. So what we're talking about is our signal's the one in black, the one that we're wanting to hear, and the difference between, I forgot to write down here, orange is noise, and here I've got my signal. The difference between the actual peak of my signal and the noise floor is what's going to be known as my signal to noise ratio. The actual overall signal is my RSSI, or received signal strength indicator. My received signal strength indicator. But the effectiveness of that particular transmission is only as effective as my signal to noise ratio. So RSSI, the received signal strength indicator, is an important thing to look at. However, noise is also a very important thing to take into consideration. And so if I have a very high level, which this is a very high level of noise, then my signal to noise ratio is much lower. And we measure these in dBm, decibels of, in fact, we're getting ready to talk about that next, decibels of, or decibels relative to milliwatts, to a unit of energy or of power. But my signal to noise ratio is going to be one of the most important factors that we're going to take a look at. It's not enough to say, hey, I have an RSSI of negative 60. Okay, and we'll talk about why negative and, negative 60 dBm. But my signal to noise ratio might be something more like negative 83 dBm. And that's really not that great at all. It's really terrible, actually, bordering on unhearable or unreceivable by the client. Okay, so if I have a signal that I want to get propagated, I could do one of two things here, right? I can either try to find and reduce the cause of noise, and if I got rid of that, I'd probably have to redraw this whole thing. But let's say we have our noise floor down here now, and this is, even though I'm using black now as a color, or the presence of all colors, it's all of a sudden my noise floor. I've reduced my noise floor because I've found the sources of those that are being too loud in my same frequency range, and I've shut them off or at least attenuated them in some way. Or I could increase my amplitude. I could put more milliwatts of power into my original transmission and make those peaks higher. And if I can do that, then even though I couldn't raise my noise floor is still quite high, I've increased my overall amplitude. And of course, this is where we get into regulatory bodies. Are we allowed to increase our amplitude? Have we violated the maximum that we're allowed to broadcast or transmit at? So if we are allowed to, of course, we would never advocate doing it if you're not allowed to. There can be very heavy penalties and repercussions if you do. But if you're allowed to, and we increase that overall amplitude, even though part of that is still in the noise floor, we now have a much higher signal to noise ratio. So maybe now we have, and with negative integers, as we deal with in decibels of milliwatts, or our transmission power ratio, negative 60 or negative even 70 is much better than negative 83. Right? Because we're getting closer to zero. So as we go, we're really increasing numerically, right? We're going to be talking about this a little more. I've already alluded to it, so let's just go ahead and look at it. Let's say I have negative 90 down here. This would be negative 80. This would be negative 70, negative 60. So we're actually increasing, negative 50, negative 40, getting to zero. And then we have positive integers like, 5, 10, 20, 30 decibel of milliwatts, or decibel of whatever it happens to be that we're talking about at the moment. So negative 90 is absolutely unlistenable. Can't hear anything there at all. Negative 50 is a really great signal. Negative 80 is bordering on not being too usable. This is typically the space that we operate in our power that we want to use. So the higher the negative number, or at least looks higher, it's actually a lower number if you look at it on a vertical scale. Okay, so keep that in mind. But we want to make sure that our signal to noise ratio is sufficiently high enough, has a sufficiently high enough decibel power rating that it's above the noise that we can hear a good enough signal strength. And signal to noise ratio is much more important than just looking at raw RSSI. And we're going to talk about how the devices measure this. In fact, how this information is even sent out in the management frames in some upcoming sections.